Hello, everybody. I am Rahima Jahel. I am a postdoctoral researcher at INRIA. With my colleague Ikan Artura from Technalia, we will present the progress monitoring of construction sites using heterogeneous data. Heterogeneous data, that means images and point cloud data. So for this presentation, we will speak first about our motivation to perform the progress monitoring and quality control on construction sites, our objectives behind that. We will show how we can perform the progress monitoring on digital twin platform, how we can make the progress monitoring automatic, and we will finish by conclusion and future work. So here we have the construction site at the first month of the scanning. The same construction site a couple of weeks later. The wall was not constructed during the first month of the scanning, but it was constructed a couple of weeks later. We want to know if the wall was constructed up to norms and on time. To check that, we need to perform the quality control in order to check if the wall was constructed up to norm, and the quality control in order to check if the wall was constructed on time. For this first part of the webinar, we will focus only on the progress monitoring. So let's now talk about the digital twin construction and why we want to perform the progress monitoring in order to monitor the construction site. You can see here in the right, the physical building twin corresponds to the current construction site. We need to monitor this construction site by collecting raw data in form of images or 3D point clouds. And in the right side, we have the digital building twin. For the digital building twin, we will interpret and merge this raw data in order to extract some significant information. This information will provide us with the project status information. For example, the as-built project and the as-performed process. By comparing this information with the as-designed projects and as-planned process, this information are given by the construction site manager. We can extract some information about the progress and the status of the construction. This information will be sent after to the construction site manager. So we start from the construction site, we extract all the information we need, we make our comparison with the as-designed, as-planned information, we extract some significant information about the current progress and status of the construction, and we back to the construction site. Now we will talk about how we can perform the progress monitoring in digital twin platform. We need first to understand the factors we need for computing the progress monitoring. We need to perform the progress monitoring in order to monitor how the construction is implemented based on the schedule. We have three possible activity level status. The first is on schedule. That means that all the elements of the current activity have been built on the same time or according to as planned. Schedule. Behind schedule, that means we have some elements build with some delay. And with the schedule, that means that we have some elements build before the planned time. If we are in the situation where some elements are not built on time or we are behind the schedule, we need to compute some quantitative information. This information will help us to predict the percentage of completion of the activity and to predict the finish date. To predict the finish date, we need first to compute the speed of the activity. To compute the speed of the activity, we have two assumptions. The linear assumption, that means that the speed is linear or uniform during the activity. As curve is assumption means that the speed is slow in the beginning of the activity, then faster, and then becomes slow by the end of the activity. Now we need to show how we can integrate the progress monitoring on the digital twin platform. So we can communicate with the digital twin platform through the APIs. What we mean by APIs, APIs are the application programming interfaces. This application programming interfaces will help us to communicate with the digital twin platform and help us to generate any nodes corresponding to the activity, extract any significant information. So we start by the assumption that the digital twin platform has all the information about the as-built element and the start and the end date of the activity related to the as-built element. So we need first to create or fetch request in order to create a node corresponding to the activity. This node will be related to as designed elements, and then we need to extract all the information related to as planned schedule. For example, the start and the end date of the activity. As you know, the as-built element is related to the operation that contain all the information about the end and the start and the end date of the construction. With this information, which represents the as-performed schedule, we compare it with the as-planned schedule, we can get the status of our construction, and with this status information, we can compute the KPIs. These KPIs will send to the digital twin platform, and we will be visualized in the dashboard in order to be able to, in order to be used by the construction site manager to make the correct decision. Now, in order to make the progress monitoring automatic, we have two axes: point cloud-based axis and image-based axis. I will present in the first part the point cloud-based axis. The objective here is to detect the objects. Why we need that? Before performing the progress monitoring, we need to check if the object was constructed or not, to be able to evaluate the status of and the current status of our construction. So to explain more the object detection based on 3D point cloud, we will start by the as-designed element. The as-designed element is an element extracted from the B model corresponding to the construction site. Given the as-designed element, we need to check to find an instance of this element in as will data or the 3D point cloud corresponding to the construction site. To do that, we need to find regions or set of connected points which share the same property with the as designed element up of given tolerance. Now the question, for this connected point, which points are correspond to the as designed element? It is our objective to detect the objects and to evaluate the quality of our detection. It is before detecting the object, we need first to collect data or to get the 3D point cloud. For this end, we have two kinds of laser scanner that can help. The terrestrial laser scanner, which have high precision, and the mobile scanner, which is faster than the terrestrial laser scanner and easy to use. In order to detect the object in a construction site, we thought to use or to propose a method based on planar polygons extraction and clustering. Why we thought we choose to work with planar polygons? Because in construction sites, most of objects are represented by planar surface. And so using planar feature is a good way to detect the objects and to evaluate the quality of our detection. We have worked with planar polygons instead the planar region, because the planar polygon has a limit surface corresponding to the area where we have supporting point in the input data, though, so the form compact and significant abstracts of the element. So the first step of our object detection algorithm is to extract the region of interest. We start by BIM model and the 3D point cloud representing the construction site were registered. With this assumption, we can suppose that the region of interest can be concentrated on the upscaled bounding box of the key elements. So when we extract this region of interest by upscaling the bounding box of the as designed elements, this region can contain several clutter or the some object that used for the construction. We need first to filter this clutter and keep only the point correspond to the element. Here we have the result of our first step for object detection. Then we need to check if there is local shift. So when we extract the region of interest and we filter it, we can judge if there is local shift or not. If there is local shift between the as designed element and the build element, we need to find this shift, then register both elements to be able to make the correct decision. If the construction or the constructed element is well detected, the detection is strong or weak, or we have false detection. Then we apply the inverse transformation in order to back to the initial position. So, as I said before, we need this comparison to be able to judge if we have false detection, for example, in case of the objects under construction. This kind of decision can be made when we have some statistical information extracted from the comparison step. Here, after detecting the object, we need to construct our volume. We construct our volume in order to use it after to perform the quality control. For the construction of the volume, we have used an external algorithm developed by our colleague from INRIA. Now we can see some obtained results on one pilot site used as part of BIM2TWIN project. Here we have the detected columns from pilot site in Spain. We see that our algorithm is able to correctly detect the columns. Here we have another result for the slabs. And for this region, the algorithm consider that those slabs is false positive. Why? Because those slabs is under construction. Here we tested our algorithm in order to detect wall from another data set. We can see that the detection is correct. And then we have a more hard situation where we try to detect the cells. We have here the as designed element, the corresponding region of interest, and then the detected object. We need to visualize the result of progress monitoring on the digital twin platform. We visualized the progress monitoring on digital twin platform via Gantt chart table. For this table, we have for each activity is presented by two horizontal boxes. The first corresponds to the as planned information, and the second corresponds to the as performed information. For example, we can start by one activity. For this activity, we have four possibilities. First, if the activity is completed with some delay, if the activity is not yet completed but on schedule, if the activity is not yet started but we have some delay, or if the activity is not yet started but on schedule. To interpret all that, I will explain for you with this table. The gray information corresponding to the as planned information of the current activity. If you have dark red, that means that the activity is completed, but is complete, but with some delay. For example, if the activity started on time, for example, in the third day of the month, and it should be finished by after 15 days, but the activity was finished after 20 days. This for this situation we have some delay. The light green means that the activity is not yet started, but we have delay. For example, if the activity before was finished by some delays, we cannot start the next activity on the correct time. And here for the green, here we have a light green. That means that the activity is not yet started, but it is on schedule. We can find another situation, it is not mentioned in this table, where the activity is not completed and on time. This kind of situation will be colored by dark green. Now, my colleague from Technalia will explain for you how we can automate the progress monitoring using images data.
Okay, thank you, Rahima. Good morning, everyone. I will share my screen. Okay, my name is Ekain, and I'm from Tecnalia, a researcher for Tecnalia. So I'm going to show you now how we our approach using images and how we obtain the data, how we proceed them to object detection, and how we show and update the digital building for the progress monitoring. So in our case, typically in construction sites, the monitoring for progress or surveillance, etc., it's made by static cameras placed on cranes or even in neighbor buildings. But what we propose now is to use an image captured with a smartphone. We decide to perform this because smartphones are accessible and easy to weigh devices where anyone can use a mobile phone to capture data without requiring specialized training. And also we wanted to try a new workflow involving the construction workers in the progress monitoring without the need for specialized persons to capture the data. So in our case, construction workers must capture photograph in the end of their workday or in the end of the task and upload them to the server that progress monitoring web platform is installed. And also say that for progress monitoring, we develop a web platform with the idea to create a low-cost solution and that will be ideal for small or medium-sized companies. So for auto detection, we use computer vision, and also we try to present an approach where we can identify a greater granularity than other computer vision solutions make. And instead of saying a binary approach or there is not, we try to detect different status, in this case for columns, but it can be used for any type or another type of construction element. So in this case, we define three different status of column with rebar, formwork, and concrete, and set them different progress. So for that, we use deep learning techniques with convolutional neural networks, and especially the YOLO, you look once algorithms. So we use different types of YOLO, version 5 and version 8 in it. So in the beginning, no public data set for concrete columns were found. So the initial work requires to annotate the images using the computer vision annotation tool. And for the first training, we use 107 images for training, 13 images for validation, and 14 images for testing purposes. To calculate the measure of performance, we use the standard metric, and this standard metric was the mean average precision or MAP. No? So for that, it's necessary to define how much overlaps the boundary boxes with the respect to the ground truth data and should be considered as successful or not. So after different trainings and using different models and adding more images obtained in Mislata pilot site in Spain, the best model that we trained was using YOLO version 8 small, and it provides us a map of 0.19. 819, sorry. So in this video, you can see that how we deploy this in a Docker file so that you can use it as a service in the web platform for progress monitoring, where we obtain as output the images with the boundary boxes of detected type of columns, and also a JSON file with coordinates inside the picture with each detection. But to calculate now the progress, is necessary to know where the picture was taken and place this in the virtual environment. Sorry. So for that, we use the data from the digital twin platform. So we use georeferenced the ISC model and also the as planned data for each for all the elements, constructive elements. No, and also from the images we use the GPS data that captured with the smartphone, and also the EXIF data where we can find different elements like the target date, also the position data, orientation, focal, FOB, etc. So what we do is like as it's known that the uncertainty of your position in a smartphone is quite. So what we try to is make like mutation carry mutations in where changing the position of the initial position, try to match the best the best result and define where the picture was taken. So for that, we use the GPS horizontal positioning error and create an area of influence to move the virtual camera and try to match the best result. And how do we match the best result? So what we do here is to use the virtual computer vision result as a reference, and with the bounding box data, we made a mask with we compare with the projection of the virtual camera on each position. So we try to find the match between the columns that was and with that, we have a predetermined threshold about the 60% or above. So to define if it's the result is correct or not. So once we know, we detect the overlapped or matched columns, what we do is identify in the ISC file which one are, and then make a call to the digital twin platform to obtain their progress. So if the progress detected for the computer vision and the progress obtained from the digital twin platform is different, we send an email alert to quality manager saying that there is advance in the construction site and inform them. And this is the main objective to do this, is because we want to speed up the validation phase and the quality managers can arrange a visit to the construction site earlier than the other way. So now here we can see the progress monitoring platform working, where we can show to the quality managers the results of the computer vision model, the image of EXIF data, 3D virtual model filtered according to the expected situation, avatar for the virtual camera, also control for virtual camera for refine the position, to the projection of the camera, and also the matching results. So what's the the goal of this? So when quality managers receive their email saying that there is a advance in the construction, they enter in the platform and see the results automatically calculated. So they have a list of detected columns with the results of the computer vision placing in it, and also the identifiers of the place when you click in if each of one, it's highlighted in the 3D model. So if they agree with this result, they can submit the data, and the digital twin platform is updated automatically. So as conclusion and future work, I will start saying, because we face commoner problems and in point cloud and also in image-based results, because one of them was like BIM models, because as we are working with GPA's data and we want to match in from the exact position, the georeferencing in BIM model is very important. They have to be well done and well rotated, positioned, etc. And also there were modeling errors also in the BIM models, because as we wanted to focus in one type of element, which is columns, the IFC class of columns was all the columns has to be this class, or even another elements like slabs or walls like were identified as columns in the building model. So when you are filtering the IFC, it makes you different, it brings you different errors. And also in planning for this kind of progress monitoring, the planning must be updated oftenly to determine the real status. Luckily, this is faced also, this is made inside the BIM2TWIN project, and you will have a webinar explaining how it's made. And also, we need in this planning a granular precision, to monitor the progress better, because if you say, okay, in 1 month, all the columns of the first floor, it will be better defining little zones and also explain the time, or split the time in fewer sorry, in less time. And for point cloud approach, Rahima, I will let you to explain this part.
For point cloud approach, our current version of object detection is able to detect columns, wall, slabs, and stairs. We want to propose an extension of this version to be able to detect any free-form object. We want also to integrate AI technique into the detection evaluation step. When we detect the object, we need to check if the object corresponds to the as designed element or the model, the element of the model beam. So we want to integrate AI technique in order to make a good decision about that.
Okay, and related to the smartphone images approach, in image quality also we faced some problems with the metadata and the GPA's precision. That's why we performed this position mutation or area scanning. And the accuracy with indoor images was impossible. We faced this approach with columns that normally we have a sky above, because you cannot create the sail before the columns, but sometimes we have some pictures to test were indoor, and it didn't work very well. So as conclusion for this progress monitoring web-based tool that we made from Tecnalia, we try to make a low-cost platform with deep learning-based object detection. Also, we proposed another workflow involving people who are already in construction site, and it's oriented to quality manager with alert system to speed up these validation steps during the construction. So the main conclusion will be like, although the complete automatization has not been achieved, these developments represent a positive step in that direction. And that's all for progress monitoring. Thank you.
Hello, can you see my screen?
Yeah.
Okay, now let's talk about the quality control. So the objective of quality control is to compare the as-built data with the as-designed data. Here, the as-built data is provided by the PCD and images collected by the LiDAR and the camera, and the design data is provided by the FC data. So our methodology consists, the input of our methodology consists of the point cloud data and the 2D image data. So my part will introduce the point cloud data-based quality control. So the first one is the as-built construction side, and the right side is the FC, is the design data. So the PCD-based quality control, we want to calculate the spatial deviation of the instance in the data. For example, we want to see whether there's any shape deviation of the column to compare these two data. So for the deviation of the wall, it consists of the length deviation on the 3 axes and the angle deviation of 2 surfaces of the wall. So how to compute the thickness of the wall? The first method is that we can directly compute the bounding box of the as-built wall. But this method has a problem that there may be some noises around the collected wall PCD data. So the bounding box will be heavily affected by the noises. So the calculation is not accurate. Instead, we may first compute the 2 surfaces of the wall, and then we compute the distance of these 2 surfaces and use this value as the thickness of the wall. So the calculated value consists of these 2 parts. Firstly, we can calculate the average sum of the distance between all the points in one surface to another surface. And then we can get the distance of these 2 surfaces. That is the thickness. And then we can calculate the angle of the norms of these 2 surfaces. That we can see whether the wall is tilted or not. So how to achieve it? We can first we can crop the object. The location of the object can be provided by the as-designed data, and we crop it from the whole PCD data to get the cropped object. Then we can segment each surface of the object. And this part has been explained by the Rahima before, so I won't include too much details. So in our work, we use the ransack-based segmentation method to achieve the surface segmentation. Then we further use the mesh reconstruction method to reconstruct the mesh through the from the PCD data. That is because the 3D models in mesh mode will illustrate clearer appearance and can be used to obtain more information. So the mesh-based result will make us to see the object more clearly. Then we also compute the shape deviation of the column. It consists of the deviation of the length and also the deviation of the angle. So we can see whether the column is vertical or not. After we calculate the deviations, we'll compare the deviations with the tolerance table, and to get whether the wall is tilted and whether the column is vertical. So we integrate our quality control. We evaluate our quality control method with the collected Mislata data set collected from the span. And this data set is also described by Rahima. So this is the output of the quality control of a wall. Our method can compute, for example, the thickness deviation and the angle. Then it decides that the wall is not tilted. And this is the output of the quality of a column. As can be seen, we can compute the length deviation and the vertical deviation. And also our algorithm can output the mesh of the object. Then we integrate our method on the DTP on the platform to make the user be friendly to interact with our method. It consists of the following steps. First, we should retrieve the data from the platform to get the PCD clusters that calculated by the object detection method, and also the design data. So after we get the data, we will input this data into the quality control method, and then this service in the interface can show the quality control results. We record a video to show how to use our interface. So first, we can click the menu to choose where the input file it is. Then after that, the platform, the interface will retrieve all the data in this folder, and then we can choose one of it. Then it can show the instance on the right side. After that, we can choose which object detection method we use to compute the point cloud clusters. Then after we click the quality control, and then it can show the object detection results of the column. And also it can show the quality of the column. For example, the length deviation and the vertical deviation. Okay, so this is the all about the PCD-based quality control. And next, we will introduce the image-based quality control.
Okay. I'm sharing my screen. Oh, sorry. Okay. So I am Maria Teresa Calcagni from Università Politecnica delle Marche. I am a PhD student, and now I'm going to introduce you the quality control of a construction site using 2D data. A quick overview on what we are presenting. So the challenges for surface textural conformance that we faced, then the developments for surface and textural conformance. After this, what are we doing and why are we doing better? And finally, we can have a time for Q&A. So you can ask all of us questions about progress and quality, and both for volumetric and surface assessment. So the challenges that we face during the development of our system, it's that what we need, what we require for conformance evaluation. So specialized personnel experienced in defect assessment. We realized that defect assessment could be time consuming depending on the extent of the building and expensive. So for the starting of our developments, we collected information and knowledge from the expert in building conformance and from the state of the art, starting on building topic and automation topic, to obtain a quality control service for classification and measurement of concrete defects. So what are we doing? We are developing a user interface for classification and measurement of concrete defects for integrate the information collected to a digital platform. What is necessary for what are we doing? So for our developments, a large data set of concrete defect images to train the AI models, and then develop the function for features measurement, and eventually using add-ons for superficial and subsuperficial defects inspections. This is, in synthesis, the required drivers and data for our system. Starting from the drivers, we need monochromatic or visible images combined with the depth devices to obtain depth coordinate, and eventually add-ons as spectral images for noise filtering, contrast improvements, and contaminants identification, and IR images for subsuperficial defects identification. Then we need to scale the data. So using the visible or monochromatic images combined with the depth device, we are going to obtain the image in dimensional unit. With all this information, we can perform acquisition and detection. So from the images, we can acquire and classify the defects and classify the defects. And combining the visible images or monochromatic images with the depth coordinate, we can also acquire the defects for the measurement. So what we are doing is create a private data set starting on buttered buildings and BIM2TWIN pilot site. In this table, you can see that we acquired a certain amount of images for each type of defect. Then these images have been given to the UNet neural network for the training, and it was evaluated with the IOU score and the model loss with these formulas. The result is in this table, in which each defect is represented with the respective score. And the best model we obtain is the one for the pitting, and the one to be improved is the one of the honeycombing. So in deep, what we are doing with our service is going on an original image and identify different kind of defects. In this case, honeycombing, pitting, cracks, and drill bar, exposed bar. In this example, we have a measurement of concrete defects. In this case, it's a crack on a wall, so the identification of the crack is performed, and we can see identification of width and length. And what we are going to collect is the timestamp, defect classification, in this case the crack, defect measurement, width and length, criticality level, in this case critical, and the defect status that could be pending or fixed when it will be fixed, pending when it's not yet fixed, sorry. Then hyperspectral can be used for signal to noise ratio improvement. In this case, we have an example of a Florence's filtration for a wavelength of 695 nanometers. And why are doing it better? Because we develop a user interface that now is used on a tablet. There could be supports to introduce that camera and additional camera on the tablet. So here is a video of a screen record of the interface. So we can or browse or select a camera for the image acquisition. In this case, we are going to load the image. Then we can insert the relative location with respect to the element of interest, and then inserting the depth value or acquire the depth value. In this case, we are going to insert to let you see all the passages. And then there is the domain. We can choose a domain of the digital building twin. In this case, we choose 1, and then start the process. As you can see on the right side, there are a few buttons in which we can enter the token for talk with the platform, the send to send information to the platform, enter the ID element, for example, of the as-built element, and connect the defect to the as-built element. So we can go on with the process, and you can see we will obtain as a result the recognition of the defects, crack with the features, width and length. No exposed bar results because it wasn't found. A very small percentage of pitting was found, but it's very small, so it's considered as 0%, and the honeycombing was not found. So why are we doing better? In synthesis, we have a defects acquisition, surface quality control tool for the processing, and finally integration in the digital twin platform. But we can see how we integrate the data in the BIM2TWIN dashboard. In fact, in this case, we are going to select a domain, in this case, Mislata, and going to the 3D progression menu, we see the entire building in consideration, and then we can select the defects. We can see the elements with the defects that we inserted, and then we can select one of these elements and see in detail which is the defect and some details. So for sure, there are challenges of AI vision-based defect assessment system, and this is a low resolution and unbalanced online dataset. Dataset labeling is time-consuming, and the application of add-ons as hyperspectral and IR camera in operating condition is challenging. But we faced these challenges, creating a private large and balanced dataset for each type of defect, and automatizing the labeling of each defect class. And we optimize the use of hyperspectral and IR measurement procedures in controlled environment. So from our side, that's all. And if you have any question, we are here to answer them.
Thank you very much, Maria Teresa.
Thank you.
We have a question on the chat. So the question is the column dataset available on the internet to other researchers?
Well, that question is for me. No, not yet. We'll see. I have to speak with the different partners of BIM2TWIN project if it's possible to make public this dataset or not.
Okay. Yeah, I know we ran a bit late, but yeah, if you still have questions or curiosities, please feel free to write them in the chat or to ask them directly. Okay, I received a question in chat for Maria Teresa, which is, what are the problems related to the outdoor use of the hyperspectral camera?
Okay, hyperspectral camera that we have, for example, is an high resolution hyperspectral camera. So it needs power supply and an homogeneous light source. And for outdoor use, we are considering in situ use. So, for example, on a building pilot site, an ongoing construction site, it could be challenging use a device like this also for dust and operators that are passing through, and it's a very sensitive device, and it's ideal. It should work in a controlled environment. So for sure, there are in market some devices that are portable, but it depends on the ranges. It depends on the different variables. So this is why we prefer to optimize the procedures in our laboratory and focus on that.
Thank you very much. And there is another question. Have you considered deploying the ontology for the construction progress monitoring? Is from a person who read the BIM2TWIN ontologies.
So maybe I can answer to this question, in fact, and the answer is yes, as this ontology or this specific aspect of the data model we have built is part of a bigger picture that will be that is already published. It has been published by the Technical University of Munich, that was in charge of leading the development of this ontology. And maybe I can provide the URL in the chat just to retrieve it. Okay. So you have in a chat the URL where to find the ontology.
Perfect. I will also copy and paste in the chat the link with information on the other webinars in case you're interested to register for the other webinars. And if there are no other questions, we can end here the meeting, the webinar.
Okay. Well, thank you, Ilaria. And thanks to all the presenters for the presentations and the explanations provided today. And thank you for the audience also.
Okay, hope to see you all to next webinar.
Thanks to
Thank you very much.
Thank you.
Thanks. Bye.
Thank you
Have
very
a
much.
good day. Bye.
Bye-bye.